Hello, everyone. My name is Gabriele Montefalcone. I'm a third-year PhD candidate at the Weinberg Institute for Theoretical Physics at the University of Texas at Austin. Today, I will talk about the freezing dark matter benchmark model for direct detection experiments. Specifically, I will consider a new regime for this benchmark where the initial reheating temperature is below the dark matter mass, and show that in these scenarios the predicted dark matter standard model scattering cross-section is significantly enhanced, making freezing dark matter more accessible to current direct detection experiments than previously understood. This talk is based on the paper I recently completed with my advisor Catherine Fries, Professor Kimberly Buddy, and Dr. Bart McShams. So without further ado, let me begin by briefly reviewing the case for dark matter. So I believe the audience is already familiar with the mounting evidence in favor of dark matter coming solely from its gravitational interaction at a variety of scale, which is very important, both at the galactic, cluster, and cosmological level. Here I portray just a few, the most famous one, such as the observed flattening of galaxy rotation curves at large radii, the bullet cluster, and more generally gravitational lensing measurements, and finally the observed patterns in the fluctuation of the CMB and the subsequent structure formation. While the exact nature of dark matter is still unknown, all of these observations constrain the main properties that a dark matter candidate needs to satisfy. Namely, dark matter needs to be cold and massive, it needs to be stable, it needs to have no to weak interaction with the standard model, and it has to be dark, hence essentially with zero very small electric or color charge. And finally, it has to be abundant. From a variety of observation, mainly the CMB, we know that dark matter today constitutes roughly 25% of the energy density of the universe, which is 5 times the amount of ordinary matter. But how was dark matter produced in the early universe? While the list I just provided seems long, the parameter space of possible dark matter candidates that fits this list is quite extensive. Here I want to focus only on the possibility that the dark matter abundance is established from interaction with the standard model BAF. The most famous mechanism by far in this category is the freeze-out story. Here, dark matter is initially in thermal equilibrium with the standard model BAF for temperatures much higher than the dark matter mass. Hence, its thermal density just follows the equilibrium distribution until the processes that kept it in thermal equilibrium with the standard model become slower than the expansion rate of the universe. At this point, dark matter decouples from the out plasma, freezing out to its final relic abundance. Here, I'm showing a plot of the dark matter yield, which is simply the number density normalized by the entropy density in the standard model BAF, as a function of x, which is just the ratio between the mass of the dark matter and the temperature of the standard model BAF. And so we clearly see that in the freeze-out story, dark matter freezes out at a temperature roughly a 20th of the mass of the dark matter. Now, assuming a weakly interacting dark matter particle with an alpha of the order of 10 to the minus 2 and a mass of the order of 100 GeV gives the correct abundance today as measured by Planck and WMAP. This fact is known as the WIMP miracle and is what motivated the extraordinary experimental efforts over the last 3 decades to target this specific parameter space. Now, the basic idea of these experiments is to look for the nuclear recoil from dark matter standard model interactions, which, in order to be detected, must exceed the detector internal background. Unfortunately, so far, we've had no detection, and overall, the WIMP parameter space is becoming increasingly constrained. In this figure, I'm showing the most competitive bounds on the dark matter nucleon cross-section published in 2023 by the LZ collaboration, which sets an upper bound on the cross-section in the order of 10 to the minus 47 centimeters squared for a WIMP mass in the range of 10 to 100 GeV. Within the framework of this experiment, there is a strong push to get to even lower cross-section, and so just go down in this plot. And to achieve this, one needs to build even larger detectors, which are already multi-ton in scale, and of course optimize all other aspects of the detector setup in order to lower the background even more. Overall, there is a relatively clear path to reach the so-called neutrino fog, which represents an irreducible background below which a direct detection of dark matter would not be possible, as essentially neutrino interaction with the standard model would completely hide the target dark matter signal. As an alternative to just pushing down in this plot is to move to the left of this plot and essentially search for lighter dark matter masses below the GeV scale. Now, conventional direct detection via nuclear recoils essentially become obsolete for sub-GeV dark matter due to the much smaller recoil energy. So for sub-GeV target masses, the more optimal strategy is to search for a dark matter signal from electron recoils. But this has only become experimentally feasible recently through developments in the semiconductor technology. Here I'm showing a picture of the detector of the Sensei collaboration, which recently demonstrated a sensitivity to single electron excitations in a silicon target, which represents currently the state of the art for these kinds of detectors. That said, while on the experimental front we've made great advancements, from a model building standpoint there are challenges to consider, and the simple WIMP dark matter picture does not work anymore. First, in order to avoid overproducing dark matter, models of sub-GeV thermal dark matter generally require some new mediator states below the weak scale. These new states must have a sufficiently small coupling to standard matter particles, otherwise we would have already seen them in numerous laboratory experiments. And in this framework, we may regard the dark matter and these mediators as comprising a dark sector, where there is also a portal link to the standard model, which may or may not be important for the thermal freeze-out. Now, in addition to this complexity, thermal relic dark matter also requires a mass above the MeV scale in order to preserve the successes of BBN. In other words, we can't really go that much below the GeV, only 3 orders of magnitude. In fact, if thermal freeze-out occurs close to the time of BBN, which is the case for dark matter close to the MeV scale, this modifies the predicted abundance of the primordial elements via changes in both the baryon to photon ratio and effective beyond the current observational bounds. Now, a very simple and clean way to get around all of these constraints for thermal dark matter is via the so-called freeze-in. The freeze-in mechanism was originally proposed in 2009 by Hall et al., and it assumes a negligible initial dark matter abundance and a very feeble interaction between the dark matter and the standard model, such that the dark matter never comes in thermal equilibrium with the standard model bath. In this sense, while the standard model is able, even if rarely, to annihilate into the dark matter, the reverse process is negligible, and the dark matter final abundance is consequentially built up gradually over time until also the forward reaction becomes negligible as the temperature drops sufficiently. For the sake of this talk, the suppressed interaction with the standard model simply arises from a renormalizable interactions of dimension less than equal than 4 with a very small dimensionless coupling. As portrayed in this plot, in this scenario, the dark matter we see is produced very slowly, with the bulk happening at the lowest temperature when the temperature is of the order of the dark matter mass. In other words, the mechanism is dominated by the IR physics and is independent of initial conditions. A popular benchmark freezing model is one in which dark matter freezes in via coupling to an ultralight dark photon that kinetically mixes with the standard model photon. The relevant interaction term in the Lagrangian is the following, where epsilon is the kinetic mixing and is a dimensionless parameter much smaller than 1. Here I'm showing the Boltzmann equation for the dark matter evolution, where on the right hand side we're summing over all the standard model particles B that produce dark matter at 3 level. On the right, I'm portraying an example Feynman diagram for these dark matter production processes, where I'm emphasizing the relevant parameter for the production rate, which is the so-called Porter coupling kappa, which is defined as the product of epsilon times the square root of the ratio of the dark and standard model fine structure constant. The relevance of this benchmark freezing model is not just in its simplicity, but that it actually represents a realistic target of the direct detection program. In fact, the presence of an ultralight mediator leads to a large enhancement of the direct detection cross-section at low momentum transfers. In the context of this benchmark freezing model, the reference dark matter electron cross-section used in direct detection literature takes the following form, where we clearly see the connection between the cross-section sigma E and the Porter coupling kappa. Now, to obtain the prediction of the Porter coupling kappa that corresponds to the production of the observed dark matter abundance today, we simply need to evolve the Boltzmann equation for the dark matter yield, given here, for a given dark matter mass, and match it to the observed relic abundance today. If we do this, we obtain that kappa must be very small, in the orders of 10 to the minus 11, which, recalling the relations between kappa and the dark matter electron scattering cross-section, it translates into this green curve on the right figure with a sigma E of roughly 10 to the minus 37 centimeters squared. Now, in this figure, I'm also plotting the current electronic recoil direct detection exclusion limits from various experiments, namely Darkside 50, Sensei, Damic M, and Panda X, and one can clearly see that the green curve representing the freezing benchmark lies at least an order of magnitude below the current experimental bounds. While there are plans for direct detection experiments to reach this benchmark within the next decade, a big challenge on the model building side is to come up with realistic dark matter models that populate the region of the parameter space that these experiments are currently probing. And to date, there exist only a very few examples, and they all require more complicated dark sectors and introduce new dark degrees of freedom. The main point of our work is actually to show that, in contrast to prior understanding, the freezing benchmark is not a curve, but rather a region, and a sizable fraction of this region already lies in the parameter space currently being probed by direct detection experiments. In fact, when obtaining this benchmark curve, we took the initial value of x, which again is simply the ratio between the dark matter mass and the temperature of the standard model bath, to be 0. This is because in the typical scenario, the reheating temperature is always taken to be above the dark matter mass. Hence, its precise value is irrelevant when evaluating the dark matter relic abundance, since, as I previously mentioned, all of the processes connecting the visible and dark sectors are IR dominated, so that the bulk of the dark matter production occurs at the lowest temperature, when the temperature of the standard model bath is of the order of the dark matter mass, hence when x is approximately 1. In this sense, as long as the initial x reheating is much less than 1, it doesn't really matter what we set it to. The final dark matter abundance is independent of initial conditions. But what if the reheating temperature is below the dark matter mass? Well, if the reheating temperature is much lower than the dark matter mass, then the dark matter production is exponentially suppressed, as only standard model particles in the tail of their velocity distributions will have enough energy to annihilate into dark matter particles that have a mass much larger than the corresponding temperature of the standard model particles. Importantly, to counteract this suppressed production rate in these low reheating scenarios, a larger coupling with the standard model is required in order to obtain the observed dark matter abundance today. And of course, a larger coupling corresponds to a larger dark matter electron scattering cross-section. So here, I present the full evolution of the dark matter yield for different values of the reheating temperature, and where we all match it to the observed relic abundance today. For illustration, I fixed m chi to be 40 MeV, and I show the standard evolution where we take the reheating temperature to be much larger than the mass, as well as 3 cases with a reheating temperature of 100 MeV, 30 MeV, and 6 MeV. As expected, for reheating temperature significantly below the dark matter mass, we observe that the dark matter yield freezes in very quickly to its final value and becomes very sensitive to the reheating temperature of the standard model. In this sense, the dark matter production process is still IR dominated, but the lowest relevant energy scale is now the reheating temperature itself rather than the dark matter mass. In addition, as we lower the reheating temperature significantly below the dark matter mass, the required proton coupling kappa increases significantly. We can understand the required enhancement in kappa analytically by solving for the yield evolution in the two limits when the reheating temperature is much below the mass of the dark matter, and compare it to the obtained relic abundance of the conventional result where the reheating temperature is much larger than the dark matter mass. And when we did that, we find that the enhancement is roughly exponential in X reheating, as one would expect from the need to counteract the exponential Boltzmann suppression. So this exponential enhancement in the proton coupling kappa associated with freezing dark matter in these low reheating scenarios of course implies that the corresponding direct detection rates also far surpass the standard freezing benchmark. In this sense, when accounting for all possible reheating temperature above the minimum reheating temperature allowed by BBN, which in our work we safely take to be 6 MeV, the parameter space opens up significantly. For T reheating much larger than the mass of the dark matter, we simply recover the standard freezing benchmark represented by the bottom green line. But then, as the reheating temperature decreases, the freezing prediction moves to larger cross sections, specifically for values of the dark matter mass below the reheating temperature under consideration. So we show here the freezing benchmark for T reheating of 6 MeV, 30 MeV, 100 MeV, and also 1 GeV as dashed green lines. As expected, departures from the standard freezing benchmark only occur for masses that are much below the corresponding reheating temperature. Overall, we find that the freezing scenario is not simply confined to the bottom solid green curve, but rather it encompasses the entire green region in the figure between the BBN bound and the standard benchmark. In addition, one can clearly see that the experimental exclusion curves now intersect the broadened freezing region, indicating that direct detection experiments are already actively probing the sub-GeV freezing scenario with low reheating temperatures. While so far I focus on sub-GeV dark matter, there is a similar story for freezing dark matter in the GeV to TeV mass range. Here, the green curve represents the standard freezing benchmark, and shaded in gray are the current nuclear recoil direct detection exclusion limits from Panda X and Xenon 1 ton. Once reheating temperature below the dark matter mass are considered, the freezing region again broadens, covering all the parameter space shown above the standard benchmark, shaded in green. For illustration, I also plot the cases for T reheating of 5 GeV, 50 GeV, and 500 GeV. And again, the story is the same. For dark matter masses much larger than the reheating temperature, the required Porter coupling kappa is significantly enhanced to values that are being actively probed right now by current experiments. Now, before leaving you to my conclusion, an important aside. In our work, we implicitly assume that the maximum temperature of the thermal bath is equal to the reheating temperature, in the sense that we simply solve for the yield evolution of dark matter in a radiation-dominated universe with an initial temperature equal to T reheating. This assumption is equivalent to the instantaneous reheating approximation and is also consistent with any reheating model that keeps the reheating temperature close to the maximum temperature, such as cases where the temperature increases or remains roughly constant during the reheating process. In red and blue, I highlighted some known examples in the literatures that achieved this, and I also pointed out other reheating scenarios such as by direct inflaton decay, that predict a maximum temperature larger than the reheating temperature. These are cases in magenta. And even in these scenarios, our framework is applicable as long as the maximum temperature does not exceed the mass of the dark matter. And with this, I will leave you with my conclusions. I hope I convinced you that in the context of the benchmark freezing model for direct detection, we cannot neglect the impact of the reheating temperature. In fact, for T reheating much less than the mass of the dark matter production rate is exponentially suppressed, so that to achieve the observed relic abundance, we need a larger Porter coupling and consequently a larger dark matter electron scattering cross-section. The possible range for the reheating temperature therefore opens up a large region of the dark matter parameter space that is already being probed by current direct detection experiments. We argue that the freezing benchmark target should be regarded as an extended region defined by the reheating temperature rather than a single curve as previously understood. In this sense, within the context of this minimal freezing scenario analyzed here, a potential future detection that lies between the current observational upper limits and the traditional freezing benchmark would directly probe the reheating temperature, providing important insights into the condition of the universe in its earliest moments. And with this, thank you for your attention, and I look forward to your question and our discussion.